Okay, so in this video, we're going to be talking about the arcsin function. This is the sine inverse function, by the way. If you're wondering what the difference is between this and sine inverse, there is none. It's just a notational thing. Sometimes some profs use them in kind of different ways, but generally there is no difference, right? We just write arcsine to avoid notational confusion between sine inverse and 1 over sine, which is actually cosecant. We'll talk about this. And by the way, if you like this video and found it helpful, remember to check out our Skool community, our online U of T and math learning community, where you can find this and many other videos on lots of cool topics, as well as attend weekly review sessions and midterm and final prep sessions, which we have a lot of, and we do tons of questions and make sure everyone is prepared and all sorts of cool stuff like that. And of course, as always, please do remember to like and subscribe. That really helps us. And yeah, now back to arcsine. We were going to talk about the arcsine function, and in particular, why stuff like this happens, why arcsine of sine of 3 pi over 2 is not 3 pi over 2, it's negative pi over 2. This seems surprising, right? This poor guy here in our graphic is having a problem with this, right? Because we want to think, right? You've seen at some point in class or on the internet or somewhere, right? You've seen this. You've seen arcsine. Let me make the pen tip a bit very smaller up here because we're zoomed in. You've seen something like this, right? Arcsine of sine of x is equal to x, and sine of arcsine of y is equal to y. And this seems nice and clean and predictable and okay, and we're all happy with this until we run into stuff like this, and then they have this kind of gotcha moment where they're like, "Oh, it's not always true, right?" And I always felt that TAs take a little bit too much sort of joy in springing this on you, right? This seems crazy, and math is kind of full of all of these little landmines that you run into every once in a while that you're not ready for. But it actually makes sense, right? These landmines are actually not landmines; they're just opportunities to see the deeper structure and ideas beneath these things. So what's really going on here is that this is kind of misleading. This is not always true. These equal signs should have asterisks, whatever the plural of asterisk is. It should have those on the equal signs, right? They are not always equal. Arcsine of sine of x is not always x. It's only true for certain x's. And same thing with sine of arcsine of y. Not always y. It's only true for certain y's. Once we restrict the domain of the sine function and also its codomain, which we talk about in other videos where we go deeper into inverses and stuff like that. Here we're going to keep it to sort of the minimum that we need to understand this for the particular case. But once we restrict the domain, then that will be true. And what's going on here is that 3 pi over 2 is not in that domain that we've restricted it to, right? That's what's happening here. Negative pi over 2 is. And these actually, sine has the same output value for those. That's what's happening. So in order to understand this, what we're going to do is look at the graph of the sine function. So this is the sine function here, which I have graphed in advance using the unit circle, right? We should know how to graph the sine, cosine, tan, and everything else from the unit circle. If you are not comfortable with those, please check out our videos on that. We want to be able to graph it, not memorize what it looks like. So we have the sine function here, and we want to construct, right? I want the arcsine function, the function arcsine. And what do we want it to do? We want arcsine of sine of x to be equal to x, and we want sine of arcsine of y to be equal to y, right? We want them to undo one another. This is the inverse relationship. The inverse relationship. I think there's an n in ship relationship, or in there's an n in relationship. So we want this to be true. And what this inverse relationship means is that function inverses send things back where they came from. They came from. Right. So whatever, and this is the key thing to it. This is the thing that we sort of skip over and don't end up understanding this always. What an inverse function does is it looks at the output. It looks at the output of a function and it says, okay, what did that function send to this output, right? The output is some number, right? So in the case of say x cubed, right? If we have y is equal to x cubed, y is equal to x cubed, or f of x is equal to x cubed. Let's do this so we can use the function inverse notation, right? If we have f inverse of, say, not 9, 27, f inverse of 27, what is this going to be? What is that going to be? Well, f inverse looks at what the cubing function, this is the cubing function here, it looks at it and says, okay, what did it send to 27? This is the cubing function. This is what it looks like. What does it send to 27? This is 3 and 27 because 27 is 3 cubed. And so it says, aha, it looks at 27. It says, what got sent here? Well, 3 got sent there. 3 got sent to 27. This is 3 down here. Try to make this a bit straighter. 3 got sent to 27. So f inverse of 27 is equal to 3. And it's that simple. So the cubing function has a nice inverse, right? F inverse of x is the third root of x. Third root of x, or x to the 1 over 3 if we do it in exponential form. And it looks like this. It looks like that. It maps every x to its third root. What about the squaring function, right? This is a very illustrative case. If we have y is equal to x squared, or again, let's do f of x is equal to x squared. And if you're wondering why we're getting off topic, this is going to help us understand the sine function. The sine function is more complicated. This is going to help us really, really understand what we're doing with the sine function. What does the squaring function look like? Well, first of all, let's see what is f inverse of 9. What is f inverse of 9? Is it going to be 3 is the question. So the squaring function looks like this. This is, if I can complete this, there we go. The squaring function looks like this. We draw the line, this is y is equal to 9 here, just like we had here. We could draw the line y is equal to 27 and see where it intersects the graph, and then take that point and find what x value got mapped up to here. If we do that here, what happened there? What's going on there? What's happening here? It cuts in two places, right? There are 2 points on the graph of y is equal to x squared, y is equal to x squared, that have a y value of 9, that have an output value of 9. And those are 3, 9 and negative 3, 9, right? When we square a negative, it becomes positive. So 3 and negative 3 are f inverse of 9, right? F inverse of 9 is 3 and also negative 3. Let me look that, then make that negative 3 look less like a bracket. There we go. F inverse of 9 is 3 and negative 3, the set containing 3 and negative 3. What does that mean? This means that this thing is not a function. Function. There we go. I can't spell when I'm doing math for some reason. Usually I can. When I start thinking about math, the spelling goes away. Why is this not a function? Well, it sent one input to 2 outputs. And one of the first things we learned in grade 11 about functions is functions have to pass the vertical line test, right? One of the first things that we learned about functions is that a circle, like say the unit circle, right? Like y is equal to, or like x squared plus y squared is equal to 1. This is not a function. It's not the graph of a function because it fails the vertical line test, right? It sends one thing to one input, one x value, to 2 output values, to 2 y values, right? We can see this if we try to solve for y. We get y squared is 1 minus x squared. So y is equal to, when we take the square root, when we take even roots, we get plus minus square root of 1 minus x squared. So if we draw a line like here, we draw a vertical line there at some point x, we are going to get 2 points of intersection with the graph. We get x and positive square root of 1 minus x squared. I should write in the positive here. X and positive square root of 1 minus x squared. And also x and negative square root of 1 minus x squared. That's what's going on here. The same x gets sent to 2 different y values, and that's not a function, right? We defined functions to have unique outputs. It's called being single valued. We defined functions to have unique outputs on some input, right? And the idea is that we want certainty. When the idea with the function is that when people say, okay, what is f of 2, they want you to say it's 5, right? They don't want you to say it's 5 or it's 10 or it's negative. Right? We don't want these like tons and tons of outputs, right? You want a unique output coming from this function. That's the whole idea. That's why we have this concept of functions, and we don't let all relations be functions. We restrict our attention to this particular class of relations, which are functions, which give us this certainty about the output if we know the input. And so this is the thing that we kind of skip over, that is not enough attention is not paid to this, right? When we are defining the arcsin function, right? People's minds just skip totally over this. We've been using functions for so long without thinking about these kind of finer points and the definitions of them that we forget about this. What is going on with this arcsin function is that if I tell you the y, if I tell you the output of the sine function, the arcsin function is supposed to be able to tell you what the input was, right? It's supposed to be able to tell you that. So if we have, and let me actually, because I just used all the space that I was going to write about the sine function, let me bring this down. I'm just going to duplicate this and bring it down, all the way down, all the way down here. Right? If we're trying to define this arcsin function, we want to say arcsin of sine of x, arcsin of sine of x is equal to x. So, but this is the thing, we don't know the x, right? We know what the sine of x is. So let's see an example of this, right? If we have, what is arcsin of 0 going to be equal to? If I'm defining this function, what is arcsin of 0 going to be? Well, what we do, by the way, we sort of skipped this thing with the. Actually, let's just go back up here for a second. You might have been looking at this and thinking, wait a second, the squaring function that does have an inverse. I know it has an inverse. That is the square root function, right? I've seen this many times. What is going on here? There is the square root function, right? Y is equal to square root of x. It looks like this. I've seen that. I've graphed that. Hopefully, what is going on here? What's going on is that this is the inverse that we get if we restrict the domain of the squaring function to make it what we call 1-to-1, right? If we restrict the domain to only the positive numbers, this and 0, so the right side of the real line here, this is why they don't put it here, right? They don't write the hidden plus there, but this is the positive square root of x. That is the inverse of this part of the graph. If we take all of the points on here, right? We take those and we exchange the x and y coordinates, right? We switch the x's and y's, which is actually the way that we graph inverses. We're not going to go into detail on that here because just for time. But actually, let me do this in different colors so we can see it. If we reflect this around the line y is equal to x, which is the equivalent of switching the x's and y's, we get this thing. We get this graph. This is the inverse relation of the squaring function with an unrestricted domain. That top part, right, this top part here, this is what we get when we reflect this piece across the line y is equal to x, right? So we would have a point here, like this would be, that's 3, 9. Let's make this 4 and 16. We reflect it across this point and we get this point, which is 16 and 4. But we also have over here, this is negative 4 and 16. We reflect that across the line, y is equal to x, and we get 16 and negative 4, right? We get also the negative square root 1, right? There are two, for this inverse function, there are two outputs for every input except for 0. 0 is the only point where there's a unique output, right? 0 gets mapped to 0, 0 squared is equal to 0. Every other number, right, you get a positive and a negative, which gets squared, a positive 2, negative 2, a positive 3, negative 3, they get squared and sent to the same y value. Right. So this thing, when we invert it, is not a function. If you ask this inverse function, what is f of 9? It'll say 3 and negative 3. What's f of 16? It'll say 4 and negative 4. It gives you two values. That's not okay for a function, right? We want it to be a function which says definitely one output for every input. What is f of 9? It's going to be 3, right? We restrict the domain here so that it's only the positive real numbers. And then we get, this is the inverse. This is the positive square root of x right here. So this sends, if this has the point 2 and 4 on it. If I say what is f inverse of 4, it tells me 2. So excuse me, what is f inverse of 2? Of 4, it's equal to 2. There we go, I'm confusing myself. What is f inverse of 4? It's equal to 2. What is f inverse of 9? It's equal to 3, right? None of this plus 3 minus 3 business. This is 9 and positive 3. So this, again, they don't really tell you this. They just kind of take this for granted. And this is one of the reasons people struggle with this so much in university. They don't tell you this in high school. But this is what's going on. This is all the stuff that's going on behind the scenes with the square root function. We had to restrict the domain in order to get an inverse. Or else the inverse will not be a function, right? They might have been talking about inverses for every function in high school. They meant the inverse relations, whether they knew it or not, right? Every function has an inverse relation, right? But not all of those relations are functions. To be functions, they have to take every input and give you exactly one output. So we have to restrict domains in some cases when we were going to get situations like this where they would fail the vertical line test. So this thing does have an inverse with a restricted domain. The idea is that, and this is now we're going to get back to this sine inverse thing, this arcsin thing. We're going to do the same thing with sine inverse. We're going to run into the same problem, and we're going to restrict the domain of the sine inverse function or of the sine function, so that the sine inverse function will be a function, right? The sine inverse relation will be a function. So there will be a unique output for every input. That's what we're going to do next. Okay, so back at last to this sine inverse function, or the sine function which we're about to invert and turn it into the arcsine function. And we're going to think, okay, we were asking this question, what is arcsine of 0? Well, when we ask arcsine, what is arcsine of 0? What it does is it goes and it looks at the sine function and says, okay, what does sine send to 0? It says, what are the solutions to the equation sine of x is equal to 0? Well, we could have x is equal to pi. I've got these highlighted here, right? X is equal to pi. We could have also x is equal to 0. We could have x is equal to 2 pi. We could have x is equal to negative pi, or x is equal to 107 pi, or x is equal to negative 2,132 pi. There we go. Right? Any integer multiple of pi, x maps, or sine maps to 0, right? Any x value, which is an integer multiple of pi, sine is going to send that to 0. So arcsine is going to look at this and say, oh, okay, well, arcsine of 0 is 0, pi, 2 pi, etc., negative pi, negative 2 pi, etc., right? There are going to be infinitely many outputs for this one input. In fact, for every sine is not what we call one-to-one. So pi over 2 gets sent to 1. Negative 3 pi over 2 also gets sent to 1, right? So each of those gets sent to a unique output, but the outputs do not have unique inputs, right? Two of these were mapped to, or two of these were mapped to the same y value, right? It is not one-to-one because it sends two to the same output, right? The squaring function was not one-to-one. It sends 2 to 1 here. The cubing function, which is invertible, that is one-to-one. It passes the horizontal line test, right? There is no y value that it sends 2 or more x's to. This one, every y value except 0 gets exactly 2 x's mapped to it. With sine, it's even worse than that. Every y value in negative 1-to-1 gets infinitely many x's on the real line sent to it. So it's badly not one-to-one. The inverse function is going to be a mess. It's going to give you an infinite set of solutions if you try to solve a simple equation like arcsine of 0 is equal to, or what arcsine of 0 is equal to. So what do we do? This is where we start to get into it. Like the squaring function, we have to pick a portion of the function which on which it is one-to-one, right, which passes the horizontal line test, and restrict the domain to include only that piece. There can also be situations where we have to restrict the codomain. We won't talk about this yet. I don't want to overload people. We want to restrict the domain to make it one-to-one. So we get to pick. We could have picked the right side here, or we could have picked the left side. We went with the positive square root. We could have just as easily gone with the negative square root and said this is y is equal to negative square root of x, and it sends 9 to negative 3, and 4 to negative 2. With the sine function, what are we going to do? We are going to pick the bit in the middle here. We are going to pick this piece. And let me put this back in just to see why we're picking this piece. We are going to pick the piece from negative pi over 2 to pi over 2. We're picking this bit here, right? We're going to restrict the domain of sine. So sine is now going to go from negative pi over 2 to pi over 2. And the output is going to be negative 1 to 1. So this is the domain. This is the codomain. It is not R. We'll talk about this in another video. Again, I don't want to sort of overload this right now. But the domain is negative pi over 2 to pi over 2. The codomain is 1-to-1, or negative 1-to-1. And now it is 1-to-1 and is what we call onto. It takes every value in between negative pi over 2 and pi over 2 and maps it to exactly one value in negative 1-to-1. It doesn't hit any twice, right? It doesn't send two x's in that range of values, negative pi over 2, pi over 2. It doesn't send any two of those to the same output, right? It doesn't hit anything in negative 1 to 1 with two or more values from negative pi over 2 to pi over 2. So on this interval, it is invertible, meaning the inverse will be a function, right? We can have arcsine of x or y, doesn't matter what variable you use for this. Arcsine of x goes from negative 1 to 1 to negative pi over 2 to pi over 2, right? It takes in values in negative 1 to 1, and it spits out a unique value in negative pi over 2 to pi over 2. So we ask it, arcsine, what are you going to send 0 to, right? What is arcsine of 0? What is it going to map 0 to? Well, it looks in this interval. Now its attention is restricted to this interval. It says, okay, in between negative pi over 2 and pi over 2, what is the only value? What is the value that sine sends to 0? Well, it's only 0, right? So arcsine of 0 is going to be 0. What is arcsine of 1 going to be? It's going to be pi over 2, right? Not negative 3 pi over 2, right? It's not going to be that as well. It's going to be pi over 2. What about arcsine of negative 1? Well, it's going to be negative pi over 2, right? There's only one value in here, in negative pi over 2 to pi over 2, that gets mapped to each of these outputs. So we have unique values for these. And this, by the way, this puts us in a position to answer that question at the beginning, that crazy, weird seeming thing. Why was arcsine of sine of 3 pi over 2 equal to negative pi over 2? This craziness. Let's bring this down here. Let's finally get some closure on this weirdness. I'll also bring down our poor friend here to finally get this question answered. Hopefully this will let him get some sleep before exams now that he knows what's going on. Why is arcsine of sine of 3 pi over 2 equal to negative pi over 2? Well, what is sine of 3 pi over 2? Sine of 3 pi over 2 is negative 1, right? So we're doing arcsine of negative 1. So arcsine, which only looks at this interval from negative pi over 2 to pi over 2 and says, okay, what number in this interval does sine send to negative 1? Well, that is negative pi over 2, right? It sends negative pi over 2 to negative 1, and that's why its output is negative pi over 2, right? And these are classic problems that they like to catch you with. They like to sort of trick you with that and get you. Those are the gotcha questions, right? People will just instinctively say, oh, of course, it's 3 pi over 2, right? I saw that arcsine of sine of x is equal to x, without this kind of, again, this asterisking, right? Which is really, really understanding the domains and the codomains. And this is the deep stuff. This is what allows us to ace tests. This is what allows us to have zero test anxiety when we go in, is taking the time to understand this deep stuff, right? And then these won't be an issue. Okay, and so hopefully this is starting to come into focus a little bit more. There's a couple things outstanding. One is, how do we graph this? I'm going to save that for a different video where we graph this and we graph arccos as well. And then arctan is actually a bit easier, but I'm going to save that for other ones because I don't want to overload this. But I do kind of owe you an explanation about why is it arcsine and not sine inverse. I didn't want to do that at the beginning and kind of delay the topic of the video answering this question, but now we can get into why is it arcsine of x and not sine inverse of x, because in high school they might have done the sine inverse, right? Well, think about this. What is 2 to the negative 1? This is 1 over 2. But this is also 2 inverse. It's 2 inverse with respect to the operation of multiplication. We call this the multiplicative inverse, because 2 times 1 over 2 is equal to 1. This is like the inverse relationship of functions, right? F inverse of f of x is equal to x. We call this the identity function. You might have encountered this concept, identity function, in linear algebra, right? The function that takes in every x and spits out the exact same x. 1 is what we call the multiplicative identity in arithmetic, right? In multiplication, anything that you multiply by 1 stays the same. It doesn't change it, just like the identity function. So this is the multiplicative inverse, right? 2 inverse 2 negative 1 is equal to 1 over 2. That's where this notation comes from, sine inverse, right? This negative one notation, this negative one exponent, meaning inverse, that's where this kind of comes from, right? But then it creates confusion, right? Because is sine negative to the negative one of x, is that one over sine of x, right? Which we know this is called cosecant of x, right? Is that what that is? No, it's not, right? Because we don't want them, because now the operation that we're dealing with is function composition, right? Not multiplication. If you multiply sine of x by cosecant of x by sine of 1 over x, you get 1, assuming that sine is not equal to 0. But we're not doing that, right? We don't want the multiplicative inverse. We want the inverse under function composition, right? We want sine inverse of sine of x to be equal to x. And again, with x in negative pi over 2 to pi over 2, we have to restrict the domain. And we want sine of sine inverse of y to be equal to y. So it's not this, and there can be confusion, right? There can be confusion about this. So that's why we come up with this word arcsine of x, this notation arcsine of x instead, to avoid that. Again, sometimes profs will actually treat them differently and say something like, sine inverse or arcsine is the one that has infinitely many outputs. So arcsine will tell you that arcsine of 0 is 0 and pi and 2 pi and negative pi and stuff like that. But and then sine inverse is the one that has exactly one. They'll tell you something like that. That's not a very useful distinction. I've always thought. I mean, there's really no point in having these things if they have infinitely many outputs, right? So it never hurts, to ask your prof if they're considering them the same. But I think like 90% of profs consider them the same. And they are supposed to have unique output, right? The whole idea about invertibility is the unique output. So okay, that's it. In the next video, we will talk about how to graph these things, graphing the sine inverse and also the cosine inverse and all the rest of them. That's a pretty interesting topic. And again, if you liked the video, if you found this helpful, please do check out our Skool community, U of T Eng Math. This is the link here. This is where you can find tons and tons more videos. Also ask questions. There are weekly office hours and review sessions, and then when midterms roll around and also finals, there are long, extensive review sessions for those where we do tons and tons and tons of problems and answer tons of questions. And there are always multiple sections so that everyone can make it and stuff like that. And as always, never hurts to like and subscribe. Thanks, everyone.